centripetal acceleration, specifically, is an acceleration that comes from a change in direction, not a change in speed. So this acceleration comes from a change in direction, not a change in speed. Now, when does a force cause a change in direction and not a change in speed? That's a tough one to visualize. Erica, give it a whirl. Oh, say it louder. A force will cause a change in direction when it is acting perpendicular to the direction of motion. All right, Jack, stand up for me, would you? Come on up here. So if Jack walks towards me, and his velocity vector goes this way, and I push exactly opposite, what do I do to his velocity? I slow it down. But if he turns and walks that way, and I push with him, what do I do to his velocity? Speed it up. So if I have a velocity vector and a force vector in the same direction, my speed increases. If I have a velocity vector and a force vector in the opposite direction, my speed decreases. And if I have a velocity vector that acts perpendicular to my force vector, I do not speed the object up. I don't slow it down. Instead, I change the object's direction. Stand up, Jack. So if Jack comes walking by me this way and I push him here, what changes? I send him flying into Lord. Oh, he's got to come by me again. He's got to come by me again to get back. I change his direction if I push him perpendicular to the direction that he is going in. Hey, how does the force vector compare to the velocity vector in circular motion? Always perpendicular. So what's always happening to the direction of motion for an object in a circle? It's always changing. And if the direction of an object is always changing, then the object is always accelerating. What do we call that acceleration? Specifically, it's a centripetal acceleration. Now here's the key. In circular motion, is the object accelerating? 100%, because it's constantly changing what? Direction. So that means when I see a circle, guess what I got to start with? Sum of the forces equals m times a. Ooh, but guess what? It's a little bit different. What specific type of acceleration is that? That's a centripetal acceleration. Which means we're going to change the idea of the acceleration a little bit. So anytime you see a circle, we don't want to start with sum of the forces equals 0 because there's an acceleration. We don't want to start with sum of the forces equals ma because I've got a specific acceleration where my number's not changing. Instead, my direction is changing. When I see the word circle, I'm going to start sum of the forces equals mv squared over r. Where guess what v squared over r equals? That equals the centripetal acceleration. Now notice, this comes from a change in direction. So this v number does not have to be changing. I could take this ball and twirl it around a circle at a constant speed of 3 meters per second. Well, up until now, What would be the delta V for an object that is traveling at a constant speed of 3 meters per second? It'd be 0. What would the acceleration be? 0. But this type of acceleration doesn't come from a change in the number. It comes from a change in direction, which means if I plug a 3 in here, am I going to get a number? I am. So my acceleration is now determined by the direction change of the velocity vector. So if we talk about our three goals here, the sum of the forces equals mv squared over r. Where v squared over r is now a particular acceleration we call a centripetal acceleration. That centripetal acceleration is always directed towards the center. Why is the centripetal acceleration always directed towards the center? Because the net force is always directed towards the center. And if you can understand those four things, then you got a firm grasp of a relatively straightforward topic.